The merge sort is at some level straightforward and another level kind of tricky because we're getting into recursion. And so tracking what goes on can be a little bit tricky, and you're going to see that here in a second. This one might take a little bit of time to walk through. Um, but each of the individual steps, as recursion often is very, very simple. And so it's not so much a deal of understanding the small steps, it's a matter of reassembling them to understand what's going to happen. So the principle is quite easy. I take a list, and if it's one item or smaller, it's sorted. You're done. Otherwise, if it's more than one item, I split the list in two. I sort the first half, I sort the second half, and then I merge those two lists. So clearly, a list of two, I deal with the bottom, I deal with the top, and then I decide what order they're supposed to go in. I merge them. They might get flipped, they might stay the same, and then I'm done. So then a list of three, again, bottom, top, and then I integrate them appropriately. And so that's what we're going to see is going to happen. Now, that simple principle, the simple code, turns into some really nasty tracing and debugging at some level. And so that's why I want to give you this visual representation of this. So same little message here, sorting fun. So now when we come in, we start off with the high, which is the last character, and the low, which is the first character. And we have to split the list in two, so we have the mid, which is the basically high minus low divided by two. So some algorithms call it left and right, center. There's different words for that, but I'm going to go with this low, high, and mid because left and right also makes sense, but the whole low and high align to the direction of the sorting as well. So I think that's useful terminology. But again, if we remember our algorithm, we split the list in two, we sort the left, we sort the right. So the right hand side between the mid and high, we're just going to ignore. And we're actually never going to sort that at this point because we'll see the principle on the left hand side of the list. And then I'll leave the right to you. It'll just take us forever to get through absolutely all of it. But on the left hand side, we now move the low and high to be the high is now the mid, and then we calculate a new mid. So we have made a recursive call. So the other low, mid, high haven't gone away. They're just back on the stack somewhere. We're going to come back to them when we return from the call we just made. Now notice our list is still more than one item. So until the low and the high are pointing to the same item, we just keep recursing. We keep diving down. So now, again, the high becomes the mid. So when we recursively call this, the high goes in the mid, and then the low stays the same. So the low and the high go there, and then the mid continues to go down from that one. So now the low is 0, the high is 2, the mid is 1. Let's keep dropping that by half essentially. One more time, the low and the high are now 0 and 1, and then the mid becomes 0 because 0 plus 1 divided by 2 is 0. So the mid's not very interesting anymore, but we do it one more time because the low and the high aren't equal to each other yet. So now that we have low and the high are equal to each other, then we know that we have a single item. We sort that single item. S is its own list, and so that call is done. So now that we've gotten all the way down to the minimum low list, the left-hand side of my array in this case, I'm going to go deal with the high part, which is also one character, because remember the last call, the low and the high was pointing to S and O. So the high part of that is O. And so that one's done. And so now I can start the merge process. And so for the merge process, I bring up a helper. I have an auxiliary, a copy of this working space. And so what the algorithm does is it starts with the low and copies everything off until it gets to the high. So it copies over 0 and 1, S and O. And then there's some logic inside of there. When you go look at the full algorithm, there's actually 4 branches. And so the branches are basically saying, what is the relationship between these indices? So if it's because remember, the idea is the left-hand branch, the low branch, and the high branch are each sorted already. And so I only need to reconcile the first of each of them to see which one is actually lower and then continue to along that process. So in this case, the logic says, okay, well, the left-hand side is greater than the right-hand side. So I'm going to copy over O. And what actually happens in auxiliary is we go from low to high in that. And so the O gets copied over, the S gets copied over, and then we're done. That call is finished. We've now merged that one. So now we've popped back out to the low is 0, the high is 2, and the mid is down here between. So we're having that next call, and we're going to reconcile that next one. And so now I copy over again. I copy over between low and high. O, S, and R come up into my auxiliary space. And again, there's these 4 decisions. I'm going to loop through each one of these and say which one does each one go from low to high. And so here, O is the same, but R is less than S. So R gets copied over, and then S gets copied over as the last one. So now I've, again, sorted this, I've merged this list and I'm sorting it as I go. The bottom list was O and S, the top list was R. The left list was O and S, the right list was R, whichever terminology you prefer to think of it. And so now I've completed that next call. And so now I'm dealing with the bottom half of the whole list. And so the low was 0, O. The high was 0, 1, 2, 3, 4, which is currently pointing to I. But I've only sorted this left half of the list. So now I have to deal with the right half of the list. So I've done between low and mid. I haven't done from mid plus 1 to high. And so I have to sort the TI first. So what ends up happening is I actually set it up with a low and high at those 2 locations, and the mid, because they're, the way it works. So this is 0, 1, 2, 3 is the low, and 4 is the high. So 3 plus 4 divided by 2 is 3.5, which rounds down to 3. So the mid is 3. So again, the same principle works. Now we're just sorting higher up on the list in between these 2 values. So now we reconcile the, let me back that up for a second. We reconciled on the list. The left list is T, the right list is I. I'm skipping over that a little bit. That would still happen in between. I'm just not showing that. And then we're merging the 2. So we copy over from low to high, T and I. And once again, we walk through these each one at a time. They're either going to be moved up directly or they're going to be compared. And so in this case, I is less than T, so I gets copied over. And then T is less than I, T is greater than I, so T gets copied over. And then now we've merged the top half of the list. All right, so notice here, the auxiliary is OSRTI, and the actual target list is ORSIT. They're not always in sync, but again, we've now done the bottom half of the list, and we've done the top half of the list, the left half and the right half, and so now we need to merge between low and high again. So we copy over ORSIT, I'm sorry, I missed that up above, but then the I gets compared with the O. So the O and the I, the bottom half of the list and the top half of the list are being compared. So the I ends up moving all the way down, then the O goes up, then the R, then the S. And so now we've blended and merged the bottom half of the list. So notice between low and mid is now sorted, IORST. And then if we continue this on, which it's not because the same principle keeps going, we would go through and sort the top of the list. So you would end up with F, G, N, N, U at the top of the list. And the same process would follow. We just, recursively would go through all exactly the same steps we did here. But then once we get down to the end, we merge the whole thing and we end up with the proper sort by having a move along. So the merge sort's pretty cool because it leverages this extra data storage to speed everything up. And it recursively sorts partially sorted lists. So it's kind of like the shell sort in that. But it has no advantage on previously sorted lists. So the shell sort tends to be, on average, a little bit quicker when things are already sorted. And it tends to be dramatically faster because of the way the shell sort works. But the merge sort here is a really great way and really fast way to be able to deal with just a nice randomly distributed list. It is markedly faster than all the rest of them that we've worked on so far, except for perhaps the shell sort, in some situations. But it does show how recursion is also a powerful tool for doing sorting. So keep working on these. This one, the code is not bad, as I said. If you are really meticulous and you nail the code the first time, you might not have to do a ton of debugging. But if you do debugging this, if you do need to debug this, it's going to be important to use print lines really carefully and be able to see each of these steps. And just remember what each of the micro goals is. It gets a little bit bigger each time, but you get down to sort the left-hand list, you sort the right-hand list, or the low list and the high list, whatever, and then you merge those two. And if you understand that principle, you should be able to knock out the merge sort before too long. But you can always reach out if you have questions.